So let's get into our last question, which is beam bending. So let's start off with our free body diagram. So I'm going to draw our free body diagram as such. I am going to set up our coordinate system, x, y, with our positive moment. And so we're going to have some reaction force. Let's just call this F1 here in this direction. There's going to be some reaction force F1, basically in the y direction here. Let's just call this x. And there's also going to be this distributed load, which we are going to treat as a point force, which is going to be Q times the entire length of our beam, L. So we're going to also have, as this goes up here, we're going to have a moment that goes in the opposite direction as such. And now we can get started. So sum of the forces in the x direction equals 0 equals F1 comma x. So we got that. Sum of our forces in the y are going to be equal to basically, or excuse me, let me draw this arrow down, although it would be flipped anyways because of our value. So equals 0 equals minus F1 and then plus QL. So that's going to give us F1 is equal to QL. So we've got that. And we also have that the sum of our moments must be equal to 0. Let's take it at the origin here. So we have basically this minus moment plus, because we're going plus Q times L squared over 2. So our moment equals QL squared over 2. So those are the values that we've got right there. So now we need to draw our shear and bending moment diagram. So let's go ahead and do that. So let's just do our cut. Actually, we could just do our base name here. We're going to do our cut somewhere here. Again, we have our distributed load. It's working all the way across here. Some distance x. Again, I'm just making some arbitrary, cut across the beam like this. Only one cut needed, thankfully. So what do we have going on here? So we have our moment here, which is going to be equal to this moment. Yeah, let's erase it. So we have some moment acting here, which is going to be equal to QL squared over 2. We're also going to have some force going this down direction. F sub 1 is equal to QL. And we're also going to have, let's get those values here. So we have this shear, V. We have our moment going around like this, M. So now we need to do sum of forces in the y direction equal 0, which are going to be equal to minus F1 minus V, and then finally plus, we could kind of dimensionalize that, Q times x. So remember, we have that QX distributed load across there. We could also do sum of our moments. The origins of them equal to 0, so I'm going to look at the origin right here. So we have basically this minus QL squared over 2. We also have basically this positive Vx. We also have that positive moment plus M. And we also have a minus QX squared over 2, because we're valuing that at x over 2. So let's go ahead and let's solve for this problem. So let's go ahead, I'm just going to create a new notebook. Let's clear everything. So let's look it over here. So we're going to say our V is going to be equal to, actually let's set, what is F sub 1? So we're going to say F1 is equal to, what's it, Q times L. Our V, it's our shear diagram, is going to be linear. So V is equal to minus F1 plus Q times X. And then we also have that our moment equals Q times X squared divided by 2 minus V times X plus Q times L squared divided by 2. Make sure that we're using all capital L's, all those good things. Alright, that looks pretty good. And we're going to go ahead and do our, again, so now we needed this expression for deflection of the beam. So we have this expression that our deflection, dx squared, is equal to m over ei. We also know that our boundary conditions, the deflection at x equals 0 is going to be 0, and our slope there of the deflection will also be 0. So I need to solve my ODE. So let's go ahead and let's look at this. Let's simplify. So now I'm going to do desolve. My equation is v dot x set equal to m divided by y times I mom, or moment of inertia. And we're going to set up some boundary conditions where v of 0 set to equal 0, v prime of 0 set to equal to 0, and I'm going to solve as a function of v of x. And let's do this. So we can take a peek at this, so I can look at our deflection. See, let's just make sure this is going to be our deflection equals. So now we can do what's our deflection at next value, or at slash dot x goes to 0. That should be 0. What's our deflection at x goes to slash dot x goes to L, where we have maximized, and we've got that value right there. So we can go and move forward with solving the rest of this problem. So we can confirm that. Oops, actually, a little bit of hiccup here. Actually, let's just make sure. QL squared over 2 minus QX. Oh, there's a 3. There's a 3 that's giving me pause here. I think I might have a little bit. Also, this is giving me a little bit of pause too. Let's make sure that we've got this right. So, when we look at our diagram, minus F1, F1 is Q times L, great, M is Q times L squared. Look at this here. Q times X. Sorry, I'm just going to double check. Make sure our math values are correct, because that 3 is giving me a little bit of a pause. Should we read minus X? Always get your signs correct. My apologies here. Because... Actually, no, this moment should be... Yes, that's... Excuse me. My apologies. So we have an error here. So let's just go back here and double check. So we have this QL squared moment that is also, yep, it's a minus. And then we also have in the same direction minus Vx plus M. And then finally we're going to have that Qx is actually going to be positive. So excuse that, a little bit of a sign error that gave us a little bit of issue. So let's go back. So let's do plus. So plus Vx, and then we are going to set plus QL squared and then minus this. So let's just do 4. I think this will be much better. Now we've got this. My apologies for that. Again, sign errors can occur. That's why you double check your solutions. So we've got those values. We're good to go now. Let's ask and see what the rest of the problem's actually asking us to do. All right, we've got this. Where is the stress of the beam maximized? So as a result of this load, we're going to be looking at a beam that looks like this. So, as such. So we know that in here, so if we're kind of basically pushing up, pushing against this is going to curve like that. We know that here, this is our center line here. And again, we're looking at this coordinate system, X and Y. So from this value of Y here, so this positive, or actually, basically in this negative value of Y, we are going to be maximized in, what is that going to be? That is going to be in tension. This positive Y here is going to be in tension. So remember, our sigma XX is equal to minus my over I. So right here, we have our moment, and then if my y is negative, again, that's going to be positive here, and then we're negative on the top here. So that's it. So we can go ahead, excuse me. So that is where we're going to be, and again, we can calculate where the moment is maximized as well. So actually, we could take this equation here, m, derivative of m with respect to x. Let's solve where this is equal to 0 in terms of x. Oops. So again, we see that at x equals L, there you're going to have that value. So you can go ahead and see where that moment is going to be maximized, and then we can kind of calculate those values out. So that's pretty much it now in these problems. So we've got where the stress is maximized. Term equation for the reduction of beam, we've got that. If instead of distributed lower across the beam, how would I, if I were to compress this beam, what would be critical load to buckle the column? Well, if we had a column and we were buckling it, we just use our P critical equation. So P crit is equal to pi squared E I over L squared. So depending on these parameters, we would kind of calculate that. If it's hollow, remember, we know that I of our hollow is going to be greater than I of solid. So we would expect that actually it doesn't buckle or it resists buckling more because we have a higher critical load to buckle, but we have that kind of local buckling stress. So beware of that in the exam. So again, beware of buckling in general, and then understanding that that hollow, how that moment of inertia changes, but that is pretty much it. So good luck on the exam, study hard. If you feel comfortable about this, you'll do great in the exam, and then again, be sure to ask questions, and good luck, and I will see you on Thursday. Great job. Thanks.